everybody. So for those who don't know me, I'm Peter Milne. I'm the old guy in R&D. And today I'm going to talk about the architectural principles at Criteo. These principles were actually announced in April this year by Anu Perron in a R&D all hands. So we're just going to do a recap today. So there's lots of words on the screen here that talk about software architecture and what it is. Let me filter some of this out for you. Just pay attention to what you see in orange. The goal of software architecture is to minimize the human resources to build and maintain a system. That's it. The design quality is a measure of the effort required. If the effort is low, the design is good. If the effort grows over time with each new release, the design is bad. It's as simple as that. So here's my agenda today. We're going to talk about separation of concerns and modularity. We're going to talk about software contracts, bounded contexts and model-first approach, command query responsibility segregation, and the notion of events, event-driven and event sourcing. Let's dive right into separation of concerns and modularity. So the graphic you see on the screen shows that separation of concerns and modularity are a function of each other. And the quadrant we would love to be in, of course, is the green one in the top right. But in the real world, we're somewhere else, and we will always be somewhere else. Let's talk about separation of concerns. So these three colored boxes represent something like layers in any solution. Naturally, most of us as software engineers build things this way: a presentation layer, a business layer, a resource layer. Presentation layer is what users or the external systems touch, like a UI or an API or a CLI. The business layer is something that actually does the mechanism of the system. And the resource layer accesses, say, persistent storage. So that's an easy way. We learned this layered architecture came about in the mid-80s, and most of us have grown up with it. So that's easy for us. Now, if we divide the separation of concerns further into domains, so here you can see we have the campaign domain and the accounts domain and the brands domain. They still have chunks of stuff that run in the layers, but they're separate concerns. So campaigns has a relationship with accounts, but they're not entangled. Brands have a relationship with campaigns and accounts, but they're not entangled. They're separate concerns. Modularity is one of the first things we learn when we learn to program. I can still remember learning about procedures and functions in Pascal in 1980 and thinking that they were magic. And most of us feel that when we write code, if we copy and paste the same code, it feels uncomfortable and we need to build a subroutine to call. So subroutine is kind of the first thing we learn about modularity. But what modularity gives us is the ability to reuse, to be interchangeable, so we can replace a modular with another one. And it is the foundation for innovation. So with some examples of this are shared libraries. We all use shared libraries. So if we're a Unix person or a Linux person, they're an SO, a shared object or a shared library. If we're a Windows person, they're a DLL. If we're a Java, Scala person, they're a jar, but there's Ruby gems and NPM packages. So you know what a shared library is. Then another concept of modularity is shared services. So service-oriented architectures or microservices or something like that. Object-oriented classes and function library packages are also considered modular. And then, of course, on the UI that people touch, whether it's a desktop or a web, there are components that we use to render information. So modularity is something we use every day. We'll talk about software coupling. So if you imagine these two cubes as being modules, you can see that there is loose coupling between the modules, the green line, and high cohesion inside the module. So the green line could be a subroutine call, or it could be an API call, or it could be a message on a Kafka queue, something like that, you can see that there is loose coupling and high cohesion, and that's good. Now, if we look at this, you can see that there's high coupling between the modules, high dependency between the modules, and low cohesion inside. This tends to suggest that these are actually the same single module and that they shouldn't be separate. Or it's just a bad design. With some mathematical formulas, you can actually look at software coupling. So the reference you see at the bottom of the screen is from the Fundamentals of Software Architecture by O'Reilly, which you all can have access to for free. And it talks about abstractness in the y-axis and instability in the x-axis. And there is a way to build a main sequence. So if your abstractness is really, really poor, but your code is really stable, you're in the zone of pain. That means every time you change something, there's a lot of pain to make it happen. If your abstractness is really high and your stability is really high, you're in the zone of uselessness. So an example of this is when the Microsoft Foundation class came out in the early 90s. Very, 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 very abstract object-oriented framework. Really annoying to use, and it was easy to be unstable. So what you want to be is somewhere in the green band. So that's coupling. We talk about cohesion. So this is a measure of what should be contained in the same module. The graphic on the right-hand side shows you water. There are a bunch of water molecules that are connected together. So each molecule is connected. So the hydrogen and the oxygen in the water molecule is connected with a covalent bond, and they're quite strong. The molecules are connected to each other by a weaker bond called a hydrogen bond. It's about 5% as strong as a covalent bond. So in this graphic, the molecules are modules, but the solution is the water that they form. Let me talk about entanglement. When you look at this graphic, you see the rope is completely entangled. It's perfectly functional. It does the job it was designed to do, but it's hard to change. In fact, it's not very flexible, and its time to market would be low. Entanglement can be obvious, or it can be implicit. For example, if you and I are separate processes running, and we share a database table, we have implicit entanglement. If you or I are separate processes running and we share an observability library, then we have an implicit entanglement. So that's separation of concerns and modularity. Let's talk about software contracts. Whole bunch of words on the screen define what a contract is and an agreement. Let me filter this out for you. A contract is an agreement that's enforceable. An agreement is harmony or accordance or a negotiated arrangement between two parties, but an absence of incompatibility. So, what's a software contract? It is the one single source of truth. For example, the signature of a method or a function or a subroutine is a contract. A remote procedure call definition is a contract. An event format or payload is a contract. Data storage is a contract. So let me give you some examples. So in the world of REST APIs, we have Open API specification. If you look at the graphic on the right, you'll see a specification of the interface to a particular suite of APIs. This is a contract. You notice that there's no code here. This is the contract between the caller of the API and the implementer of the API. If you look at this one, this is a GraphQL schema definition language. Same kind of strong contracting language, which means the consumer of the GraphQL, the person issuing the queries or the mutations, is abiding by this contract, and the implementer of the contract is abiding by the contract. So let's look at another one. Let's look at protocol buffers. We've all touched these somewhere in our lives. These are great for messages or events or file formats or gRPC, which is a kind of RPC. In protocol buffer, you specify the shape of messages, their relationships to each other, and also sometimes the operations that can be done on them. This is a kind of software contract. Once again, note that there is no implementation here. It is the specification of the contract. And we've all done this. Data definition language in relational databases. This is where we talk about what we're going to store in a particular table and possibly its relationship to other tables with the foreign key. We aren't telling the database how to store the data, whether it's stored as blocks on a disk or whether it's stored as files on a disk, how they're compressed. We don't care. This is just the contract we have with the database. So that's software contracts. Very important. Let's talk about my favorites, bounded contexts and model first. We'll start with bounded contexts. What's a bounded context? Well, let me talk to you about this graphic, domains, contexts, and models. These blue circles represent a domain model. The one indicated on the screen is a domain model for a user, but you see others of identity and document and policy and reporting. We can group these domain models or these models into domains. So we have a life insurance domain, we have an IAM domain, and we have a back office domain. These are chunks of work, chunks of functionality. This is something that's probably specified to you by the product owner. If we take these and we draw these red circles around one or more of the domain models, we have a bounded context. And a bounded context is a chunk of work that is developed by a group of developers who work together, so a team. It means they focus specifically on this bounded context, and their cognitive load is lower because they're experts in user or experts in identity. They know about customers or reporting, but they don't need to know the details. So what you do is you surround a bounded context by one or more software contracts, sometimes between subcontexts. The contracts specify the interfaces to the bounded context. Does this make sense? I hope so. Okay, let's talk about model first, and my catchphrase here is think before you code. So what you see here is a model of an Airbus A380 with the Lufthansa livery on it. And what you see here is a real flying Lufthansa A380. They're related to each other. So a model is a first-class artifact. It's a representation of the finished solution with some details removed, like the model in this has some size removed and the engines don't actually work and there's no seats inside, but it gives you an idea of exactly what it is. It's semantically rich. It should be a semantic rich equivalent of a product specification or requirement. It's the source of truth. These models are important and we're very good. We're all very good at not making them. There are two kinds of models. There's a canonical model and a physical model or a logical model, and I'll explain what these are. So the canonical model in the red circle in the center defines the entities and structures and relationships and operations. So in the case of ad tech, we have campaigns and line items, and we have buyers and sellers, and we have accounts, and we have brands, and we have advertisers, and we have creatives. All of these things are entities that are related to each other in some way. Physical models, sometimes called logical models, are the contracts. So in this example, we have derived a physical model from the canonical model, and we're going to produce, say, an API specification or a protobuf specification or a GraphQL schema from it. So they are related to each other. Let me elaborate a bit further. So on the left-hand side is a canonical model. Most of you have seen these something like an entity relationship diagram or a class diagram. It's the canon of truth. It is what we actually want, often defined or specified by a product owner. In the center, you see the physical models. These are our rich specifications. So if we wanted an API to access a line item, a REST API, then we would take the canonical model and we would build a structure in Swagger to produce the contract. And then we would take those contracts onto the right-hand side and produce running code, deployments, services, processes, SDKs, databases, whatever. So that's contracts. Let me talk about command, query, responsibility, segregation. The person on the left is giving their dog a command. In our speak, it might be create ad set, activate ad set, compose audience. On the right-hand side, the person is asking their dog to shake. So this might be the equivalent of list ad sets, ad set details, list audience. One is a command and the other is a query. So cause, or CQRS, not cause, CQRS separates the read from the update. It's as simple as that. So the CRUD pattern, which is create, read, update, delete, or insert, select, update, and delete, is where we've taken a canonical model and we build read and write models from it, and it's all the one thing. This is your classic application that talks to a database. The CQRS pattern separates the command model, the write model, from the query model. So you take the canonical model and you generate specific, or you derive specific models for commands and queries. In this example, we've got them in separate data stores connected by events. That is a possibility, but it's not a requirement. So what circumstances do you do this in? It's the problem is when you have your data model has become super complicated. You've got many variations of a query, or a complex, sophisticated object graph becomes the results of your query. You've got complex business logic, like creating a campaign can take a lot of work. It's not just as simply writing the data. There's some other things that go on. The workloads are asymmetric, meaning that the performance requirements of each side is different. And you have a lot of data contention. So the solution is you build commands that are task-based. They can sometimes be placed in a queue and processed in order. Queries never modify the database, they're just read. So think of them like a materialized view. And the models can be isolated. You can actually have different code doing two different things. So instead of having a service that does both, you might have 2 or 3 different services that achieve the same thing. So when would you use it? When you need data access and in parallel at scale. And in parallel at scale is a subjective statement, and you have to think that through. So don't use it if the business rules are simple. If CRUD works, just use CRUD. You only use these advanced techniques when you get to the point where your database or your services don't deliver. Okay, so now let's talk about, I'm running out of time, but we'll talk about events. So the graphic on the screen, you can see a command is being issued on the left-hand side to the dog, like activate ad set. And then when the ad set is activated, an event is emitted to anybody who's interested in receiving it. So by definition, an event is a significant change of state. It happens. So that's the definition of an event, emitting an event. So event-driven is where you start, say, with emitters of an event who are saying that something happened, like the ad set has been activated. And then the emitter of the event doesn't care or doesn't know or is ignorant of who the consumers are. So the consumers or subscribers are waiting for this event. There may be no one, or there may be 1,000 subscribers. And they're going to do something with that. So if it was a UI component, it could re-render the component. If it was a bidder, it could then act on the fact that the ad set was activated. And then, of course, you have a channel by which the event moves. So we often think these as pub-sub frameworks, but Kafka works really brilliantly at this, and we have a lot of talent for it. But the channel is just as important, particularly with an event store that is persistent. So that's event-driven. Let me talk about event sourcing. So this is Martin Fowler. If you've not read any of his books, they're worth reading. So event sourcing is where you have a bunch of changes to state that occur as a sequence of events. And to reconstruct the past, what you can do is you read all of the events. Let me show you an example of this. So on the left-hand side, you see somebody creating a cart and adding items to the cart and removing items from the cart, adding shipping information. All of these events are stored in sequence in the event store. And then somebody clicks the buy button, and we go through those and we materialize the cost and the delivery and where it's going to go. So that's the way event sourcing works. So we've talked about events and event-driven, and this is a more sophisticated pattern. So if you have a problem where the latency of your CRUD system is high and your concurrency is low and your scalability is low, then the solution could be to use something like event sourcing, which is typically low latency, high concurrency, and high scalability. The graphic on the left is a bank statement. So imagine your bank statement. Every transaction you do is written immutably into a data store, and your account balance is actually processing all of those events in sequence to give you a number at the end. And this is the way banks have worked since my grandfather was alive. So considerations about event sourcing. Things will be eventually consistent by replaying events. The system has to be able to cope with a lack of transactions. So you need to use event sourcing. You notice that there's not going to be the whole concept of an atomic transaction. It's eventual consistency. And you may find that your events will be published or more than once. They'll be at least once, but your actions should be idempotent, which means you can go through the events each time and realize that you don't have two different events. They're just a copy of one. So event sourcing is quite powerful, but we use it in the right place. Okay, so I've talked to you about these 5 principles: modularity and separation of concerns, software contracts, bounded contexts, and model first. Please build yourself contracts and bounded contexts and allow you time to sleep at night. It'll make your life easier. CQRS is a way to separate your concerns. This is a great way if you have asymmetric workloads. And event-driven is something we can use. Event sourcing is something we do when we need to. So let me give you some advice. The graphic on the left is a shanty town. The graphic on the right is a beautifully planned city. So the shanty town on the left is how we build software in a startup. Note that the shanty town actually works and makes money. People live there, they live their lives, they produce goods, they're happy, they enjoy themselves. The problem with a shanty town is when you change something, it has an effect on so many other things. So if you wanted to put in a sewerage system through the shanty town, it would affect everybody. Everything would have to change. On the right-hand side is this beautiful city planning where everything's done in advance and it's perfect and it's gorgeous and wonderful and it's easy to change and everybody can enjoy it. Well, that's where you have an enterprise architecture team. And I've worked on enterprise architecture teams and they're not as pleasant as you think. Somewhere in the middle between being a shanty town and a beautifully planned city is the sweet spot. It is what we can afford to do to give us the least amount of pain when we make a change and to be able to be agile enough to move to what our product brothers and sisters require us to do in the future. But in software architecture, there are no easy decisions. You always have to choose a compromise, and sometimes you're choosing between two unpleasant things. You're looking for something that's the least unpleasant. There isn't a quick, easy decision. I want to warn you that no good implementation can fix bad architecture. So to be very blunt, the most perfect, efficient C# code that's written beautifully and everybody likes will not fix problems associated with a bad architecture. You have to fix the architecture. And my last statement is, I want you all to think before you code. Thank you for your time.